Hi everybody, today I want to talk about the Lyapunov equation or an LTI stability issues. First, for a given x dot equals ax type of system, what we want to know first, we want to know is this system, dynamical system, stable. And there are a couple of variations of stability, of course, but today I'm gonna only talk about LTI stability. And since this is LTI, when we talk about the stability, we mean global asymptotical stability. Okay, because here asymptotical stability in the case of linear systems implies global asymptotical stability because there's only one equilibrium point. All right. Now, first, for this system to be stable, all of the eigenvalues of A matrix must be lying in the wait a sec, open left half plane. Okay, this is real imaginary. For example, eigenvalues can be like this of A matrix, of course. All right. If we look at the eigenvalues of the A matrix and we see this type of situation, we conclude that the given dynamical system is stable. All right. However, the eigenvalue problem, the computation aspects, I guess, is not numerically stable. So we, for the higher dimensional systems, of course, have the tendency to use another type of theorem, which is called, which is called theorem is stable if there exists P such that A transpose P plus PA is less than 0. Okay, if we have that kind of P, that will imply that the given dynamical system is stable. Okay, so let's discuss this theorem a little more. Here, what we want is the P to be positive definite. Okay, this is first condition, and here this is the second condition. Let's extend this result. Okay, this is negative definite. Okay, so let's add some positive matrix so that this becomes 0. Okay, when I say 0, of course 0 in the sense of matrix representation. Okay, and here the other constraint, we add another constraint, which is Q to be positive definite. All right, and we can write just to arrange the terms. Okay, and also P and Q are symmetric as well, on top of being positive infinite. Okay, and if you're interested in control, you probably know that this is Lyapunov theorem, which is the following. For any given Q, we can find there exists P such that ATP plus PA, let's write this in this term, okay, such that there exists unique, I made a mistake, wait a sec, there exists a unique P positive definite, which is positive definite, such that this given equation is satisfied. Okay, so now the numerical or computational aspects of this, the determination of stability, how we will go about proving that a given system is stable. Well, first you can just check the eigenvalues. Second, if you like to be more numerically accurate for a given real high dimensional, I mean, I don't know when you will need that kind of numerical computation or accuracy. Maybe more than 10th degree, 10th dimensional systems, you might like to have that. Anyway, let's talk another issue. You can use YALMIP, which is a MATLAB toolbox for LMI, linear matrix inequality computations. This is, I mean, YALMIP has a website and it is easily downloadable, and you can just add to MATLAB as any other MATLAB toolbox like robust toolbox and control toolbox, etc. And another issue, if you don't like to use YALMIP, or I mean, there is also Lyop command in MATLAB. This is just, you don't need to use any kind of toolbox for that. And you can use also, there is another Sylvester theorem, Sylvester equation based theorem. Let me expand it on this. Wait a sec. Here let's talk about Sylvester equation, which is, I mean, of course there are other variations of that. This ax plus xa, I mean, Hermitian, but we can just here in this case use transpose plus q equals 0. Okay, the theorem is the following: given any q which is positive, there exists a unique p which is positive, such that let me write this here: a transpose p plus pa plus q equals 0 if this given equation is satisfied, condition is satisfied, if and only if this implies the given system, dynamical system, is globally asymptotically stable. Okay, and you probably this, I think this sounds familiar to you at this point. Okay, let's focus on, wait a sec. Well, before expanding on this a little bit, let me talk about a little more on the Sylvester. It's hard to write this. Sylvester equation and Lyapunov equation. Okay, the Sylvester equation is the following. Just this is new chapter. This is new section. All right, let's just only focus on. Let me delete this. Let's just only focus on ax plus xb equals c. Okay. Let me also give the dimensions. A by n, b, then m by n, m by m, and c n by m. Okay, just keep that here. We can wait a sec. Yeah, just here only focus on, you know what, let's think x as x1, x2, and x3. Okay, and x1, x2, x3 are the columns of X matrix, and let's just write here x1, x2, x3, and B matrix just do the same for B matrix as well. B1, B2, and B3, right? And equals C. Yeah, we can do same for C. 3 is a good number for, you know, to show the kind of relations. Here, just only focus on the first columns of the term. All right. Here, A x1, okay, plus let me, how should we do that? Yeah, just write x, okay, just b1 equals c1, alright, and a x2 plus x b2 times b2 equals c2, and I mean, I know I'm cognizant of the fact that, yeah, this might sound boring at this point. Okay, yeah, and let's write them in sigma notation. AXI plus XBI equals CI. Of course, you can conclude this from this using 3. You can convince yourself this is correct by using this 3 given column notations. Okay, equations, and here this is also equals to, let me write this here, AXI plus, yeah, this is like the critical part, J from 1 to M, B J I X J. Okay, and let me write this. Yeah, let's get this here, and A plus, let's write this in a matrix form. Okay, A plus B11 identity, of course, because of the dimensions, and since there are 3 columns for each matrix, let's write this here in this notation. B21 I, okay, B31 I, okay, B I, A plus B20 I 22, and B 32 I, okay, B13 identity, and here B23. Wait a sec, is this zero? Yeah, 0, and A plus, again A plus B33 identity. Okay, what does it equals to? It's equals to, let me write this in this notation, x2 and x3. Let's only think as if x has 3 columns, x matrix. Alright, and what does it equals to? C1, again the same notation, following the same notation, C2 and C3. Okay, so at this point I mean, we just write this equation in this matrix representation, and after that it all follows easily. And let me say this, we need to find this matrix, and we know this matrix. Why do we, let's get behind this. Yeah, why do we know C? Here, what's the C? C is this, and let me remind you that we are going to use C as the Q in the Lyapunov matrix equation. Okay, so, and let's remind ourselves the theorem, which is, we know Q for a given positive Q there exists a unique P. So we know Q. We are going to supply this machinery, the Q positive Q matrix, and we are going to solve for P matrix. Okay, and then check if the P matrix is positive definite, and then we are done with proving the stability of the dynamic systems. Okay, I know I'm iterating over and over, but this is kind of, yeah, the main source of the contention. And here, so we know C matrix. Let me write this. We know this, it's known, and we want to know, this is unknown, and let us remind ourselves what is B and A in this construction. A is the, first of all, we are going to use A as A transpose here. Just look at this. The similarity between the two matrix equations. Here, A transpose. Okay, this might sound confusing to you, but that's okay. You're going to get used to it. And B here, in terms of this matrix, will represent A transpose. Okay, so what I'm trying to say is this: we know A, quote unquote A, and quote unquote B. Okay, so this matrix, this is canonical product matrix. Of course, this is dilated. This is a big matrix. Let's say we have n by n n-dimensional dynamical systems. This is like n square by n square matrix. Okay, it's sometimes called dilated matrix too, and this is known too. This is just not known. And let me abuse some notation. This is always almost like, let's call it A bar plus X bar equals B bar, right? This is known. This is known. We want to know this, so this is it. This is just we managed to reduce to proving the stability of a given dynamical system, LTI dynamical system, just to a simple matrix inversion operation at this point. Okay, so let's talk a little bit about this too. Here, let me write this. AX plus XP. By the way, without writing this, let me represent this last equation. Just let me do it down. Last equation in a common notation, and which is let me check my notes. Identity canonical product A here again, AX plus XP equals C. AX plus XP equals C. AX XP equals C. We are focusing on the, at this point, Sylvester equation. Okay, and canonical product plus B transpose canonical product identity vec. I'm gonna explain this symbols and notations. Okay, here the first one, canonical product. I know my writing is not the best. Okay, and canonical product is, let's say, A11, A12, A211, A times B matrix, which is like 2 by 2. Okay, but let me just write in B, not B11 and B etc. And canonical product is this A11 times, and this is scalar, A11 is scalar, okay, times B, okay, A12 B, A21 times B, A22 times B. Okay, so we just dilated the A matrix, and pointwise multiplication operation will result in this canonical product. This is just for the notation, for the sake of having some good notational operation. okay, or the good notation for the operation we want to perform. And here again vec dot this operator. This operator is like, yeah, let's just write this. I mean, I feel like you might guess what it means at this point. And this is A11, A21. Yeah, this is like just okay, and A12, A22. Okay, and you probably know this from MATLAB's dot operator, right? But again, whenever you use this type of operation, please just look at the document and check if this library is doing what you want it to do. Okay, because there are some dimensional and for example, let's just say 1, 2, 3, 4, 5, 6, 7, 8, 9, and this is A. Okay, when I use MATLAB and type in this comment, I will get a vector which is like 1, 2, 3, 1, first column, second column, and third column, 3, 6, 9. Okay, yeah. However, this is not that irrelevant at this point, but let me 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, when I use actually this is like reshape A 2 by 2 or 2 by 6 by 2. Okay, let me just write this a little bit more clearly. And where is it? Let me use this cool stuff. Okay, here when I use, there's another comment which is reshape, which is a bar equals reshape A 6, 2. Okay, it does 1, 2, 5, 1, 2, 3, 4. There are 4 columns, and 3, 4, 6, and 7, 8, 9, 10, 11, 12. It does this operation. Okay, and this is the A bar, and this is 6 by 2. Okay, so you know, just check the documentary of the MATLAB and use reshape cautiously, I must say. And this was a big detour, I realize that. And let me just turn back here and justify this equation at this point. Here, when let me use just copy and ax plus xb equals c. Okay, this is like the final stage, and again Sylvester equation, ax plus xb equals c, and oh, did you forget that? Okay, one more time, copy, paste. All right, when we have this type of equation and we know a B and C, and we have this equation. X is given by this computation. Okay, so let's apply this to what we have, the Lyapunov equation. Here, A transpose P plus PA equals Q. Alright, just translate this. Here, identity, Kronecker product, and here A is like wait a sec, A transpose A transpose, and B is PA, B is A, okay, plus, and since it says B transpose, we use A transpose, Kronecker operation, identity, and vector P equals vector operation Q. Okay, so okay, let's now go to MATLAB and check the check a simple example to prove and show ourselves that this is in fact correct. And let me just write something, let me just say something. I get this especially the Kronecker product and Lyapunov equation Kronecker product computational aspect of the content of this video from the given book, Matrix Analysis for Scientists and Engineers, and the writer is Alan J. Loeb. Okay, and also I must say my inspiration, I get my inspiration from the lecture video that I watch on YouTube from I guess the lecture code is MAE 598, and this is called LMIs in Control from Arizona State University by Matthew Pitt. Okay, let's just focus on and do MATLAB examples. Okay, wait a sec, let me get this, and here, okay, here this line is needed for YALMIP, and you can check the website. It's really easy to integrate your MATLAB, and we don't need to use B, by the way, but let's just focus on A, and let's check A. Here A is like a 6 by 6 matrix, and let's check the stability of this A matrix by just looking at the eigenvalues. And here we can see all the real parts of the eigenvalues of A matrix is negative, and thereby eigenvalues of the A matrix lies in the open left half plane. And okay, and let's solve this problem, the Lyapunov problem, or let's just get a P matrix such that P is positive definite and A transpose P plus PA is negative definite. And this is the YALMIP command. Here, this is just given in the YALMIP website. Just clear the memory of YALMIP operators, I guess. This is needed, just ignore this. Like, consider, you might like to maybe consider as a cleaning the cache. And here we just use the stp var command, which generates or which initiates P as 6 by 6 symmetric definite positive matrix. Okay, and here this is used to impose this constraint on the problem. Okay, just identity. Okay, let me show this. Just some epsilon times identity. Okay, just you might like to think that way. And since this is a strict inequality, and we would like to have, of course, non-string inequality, meaning equals and greater types of representation or equation, we just write this in this form. And this is the first constraint. Okay, and this is of course the concatenating the other constraint. And the second constraint is this: A transpose P plus PA is less than or equal to 0. Okay, you might maybe thinking, hey, why didn't we use just less than? It wouldn't be numerically stable. It wouldn't be kosher in this case. And you might be thinking, hey, maybe P is not that negative or positive definite, but we guarantee that P will be positive definite, and maybe this is not negative definite, but after that we will check that, but this is guaranteed to be working. Okay, and here we just add the appended this constraint on F, which is the constraint or object, which is constraint object. We use this constraints and optimize over these constraints and find a feasible P matrix. Okay, let's just run this. Okay, and YALMIP is complaining about something. Let's just run this. This is the feasible P, and let's look at the eigenvalues of P feasible, and this is all positive, which means P feasible is positive definite. Okay, let's check another constraint, which is this: A transpose P plus PA being negative definite. Okay, let's just check the eigenvalues to see if they are negative. Okay, they are negative definite. This is, and which implies A is Hurwitz and the given dynamical system is stable, global asymptotically stable, because it's LTI. Okay, and let's just focus on the second solution aspect of this video. Here, let's remind ourselves that this is we are going to use this. Maybe use that. Okay, we are going to define Q as identity, and since this is 6 by 6, okay, and then wait a minute, I made a mistake, I'm sorry for that. Let's just say negative Q and negative Q. Okay, and I just call this in the MATLAB VQ. Okay, first I define VQ, and then I define this big derivative matrix, and then I solve for P, and then I reshape P to get 6 by 6 P positive matrix, and then I check if the whole computation was correct. Okay, let's clear off. Okay, sorry. This is the A matrix. Let's define that. Okay, and this is Q, and this is VQ, and this is 60. It has 36 entries, and here the corner curve is, let me get this, and here this is the corner curve operator, and this is exactly the same thing. I just write exactly the same thing: identity A transpose, okay, plus corner curve A transpose identity. Okay, and this is, we need inverse of it, this big matrix, and we're going to multiply this with this VQ term to get P, but vec P we call here, and I call it temp P, and temp P we're going to reshape that to get P matrix. That's why I explained the intrinsic aspects of reshape command here. Okay, let's just run this. Okay, let's look at our P matrix here. This is it, and let's look at if the given computed P matrix is positive, definite. Here all the eigenvalues are positive, since P matrix, we conclude the P matrix is positive, definite. And let's check the eigenvalues of the A transpose P and PA plus PA to expression. Here, this you might consider this as, you know, some numerical errors, but all in all, this is negative definite matrix, and we conclude at this point the given A is service. Okay, and this is the end of the video. Thank you for watching.